All right, so this is the task we did in class, cafeteria actions and reactions. So we're developing some concepts here about solving equations. So Elvira, the cafeteria manager, has just received a shipment of new trays with the school logo prominently displayed in the middle of the tray. After unloading 4 cartons of trays in the pizza line, she realizes that students are arriving for lunch, and she will have to wait until lunch is over before unloading the remaining cartons. The new trays are very popular, and in just a couple of minutes, 24 students have passed through the pizza line and are showing off the school logo on the trays. At this time, Elvira decides to divide the remaining trays in the pizza line into 3 equal groups so she can also place some in the salad line and the sandwich line, hoping to attract students to the other lines. After doing so, she realized that each of the 3 serving lines has only 12 of the new trays.
That's not many trays for each line. I wonder how many trays there were in each of the cartons I unloaded.
So, what we want to do is help this cafeteria manager answer her question, okay, and explain how we can do that. So, if you're working on this at home, pause it right now, take a few minutes, and try to figure this out on your own, because that's where the power is going to lie, instead of just seeing what I do. And then unpause it and see how we did. Okay, so if we're looking at this, we should know that we're starting out with 12 trays, right? That's how many we know. Then we know that she split them into 3 equal groups, okay, which normally would mean division, right? But we're working backwards, okay, so that was dividing by 3, so we're working backwards, so we want to start by multiplying by 3. So we get 12 times 3, and that gives us 36. Okay, so if we keep reading, we know that 24 of those trays were taken out before she split them up. So in the story, 24 were taken away, but since we're working backwards, we want to do the inverse, so we would actually add 24. Okay, and then that would give us 50, 60. Okay, so she unloaded 4 cartons of trays. Okay, normally unloading the 4 cartons would be like multiplying by 4, but because we're splitting them back up into the cartons, we would divide by 4, giving us 15 trays per carton. Okay, we could write it if we wanted to as a full-on equation. Okay, 12 times 3 plus 24, and all of that divided by 4. Okay, which, if we were thinking about it, we could have also said we had X number of trays, so we times that by 4, subtract 24, and then that whole thing we divide by 3, and those would be the inverses expressions of each other. Okay, so moving on, the same concept here. Elvira is interested in collecting data about how many students use each of the tables during each lunch period. She has recorded some data on post-it notes to analyze later. Here are the notes she has recorded. Some students are sitting at the front table. She gets distracted and didn't record how many. Each of the students at the front table has been joined by a friend, doubling the number of students at the table. 4 more students have just taken seats with the students at the front table. Then the students at the front table separated into 3 equal-sized groups, and then 2 groups left, leaving only 1/3 of the students at the table. As the lunch period ends, there are 12 students seated at the front table. Elvira is wondering how many students were sitting at the front table when she wrote her first note. Unfortunately, she's not sure what order the middle 3 post-it notes were recorded in, since they got stuck together in random order. She's wondering if that matters. So in other words, that's her first post-it, her second and her third, her fourth and her fifth. Now, this one she knows was first. This one she knows was last, but the other 3 she doesn't know the order. So our question is, does it matter what order? Okay, so again, just like with the trays, we want to work backwards and see if that order matters. So we want to try it a few different ways. Okay, so again, pause it, try this on your own and see what you get, and then take a look at what we've got here. All right, so if you think about it, there's honestly 6 options that you could have done. Okay, so in order, you could have went the natural order that the notes were written down in our information. You could have swapped 3 and 4. You could have started with 3, and there was 2 options for that. Or you could have started with note 4. Oops, that should be 4. Okay. So, on each of them, we know we started out with 12, right? And if we think about this, okay, if this were x, and depending on which order we were going, note number 2, doubling, would have been multiplying by 2. 4 more just took their seats, that would be adding 4. And then separated into 3 equal-sized groups and 2 groups left, that would be dividing by 3. However, when I'm working backwards, I'm doing that inverse operation. So really, I would be timesing by 3 here. So each 4th group would be timesing by 3. Okay. Then if I look at group 3, it would actually be subtracting by 4 would be the inverse operation. So I should subtract 4 each 3rd time. Okay, and then finally, instead of timesing by 2, I should really be dividing by 2 if I'm working backwards. Okay, remembering that we're working backwards here, so we have to do the inverse operations. Okay, so if I start with 12 each time, okay, you can see what we get. So 12 times 3 would be 36, minus 4 would be 32, divided by 2 would give us 16 students at the beginning. Okay, let's see if we get 16 for the rest, because that's really what we're checking, is to see if this order matters. So 12 minus 4 would be 8, times 3 would be 24, divided by 2 would be 12. So those weren't the same. 12 times 3 would be 36, divided by 2 would be 18, minus 4 would be 14. 12 divided by 2 would be 6, times 3 would be 18, minus 4 would be 14 again. So 2 of them kind of seemed to work the same way, didn't they? Okay, 12 minus 4 would be 8, divided by 2 would be 4, times 3 would get us back to 12. And then 12 divided by 2, 6, minus 4. Minus 4 would be 2, times 3 would be 6. So we can see that we do come up with a few that are the same, but overall, they're not the same. So does the order matter? Yes, the order does matter, which when we're talking about solving equations, it does. And we can see that more explicitly here with these equations. So these equations, these 3, deal with these 5 notes. Okay? So if we're solving them, like this first one, to get that x by itself, first I'd times both sides by 3, coming up with an equivalent equation of 2 times x plus 4 equals 36, right? My x's are going to be the same here. The reason I know they're the same is because I did the same thing to both sides to undo it, okay, that inverse operation. So then I divide by 2, giving me x plus 4 equals 36 divided by 2 is 18, minus 4, and I got x equals 14. So if I go back up here, it looks like that was this version, wasn't it? Okay. But if I look at the next one, same steps, just in different order. Here is I first divide by 2, and that gets me x divided by 3 plus 4 equals 6. Then I subtract by 4, so I get x over 3 equals 2, times by 3, and I get x equals 6. Okay, definitely different answers. Okay, that was definitely this last group right here. Okay, and then finally, I times by 3 first again, giving me 2x plus 4 equals 36. But this time I subtract 4 first, making these equivalent equations. So that's 9, right? 36 divided by 4, or minus 4. Whoa, I went divide. What was I thinking? Now it's 32. way off there. Divide by 2, and I get x equals 16. Okay, again, that was represented by our first one. Okay, so those 3 different steps in different orders, as we can see mathematically, definitely is different. Okay, so the idea here is we come away with that when we're solving equations, we have to do inverse operations, and it matters the order, so we have to work backwards. Okay, we create equivalent equations, which we use to find the simplest form so that we get the easiest answer. Okay, but all those concepts that we just saw here, we need to use when we're dealing with solving equations. Okay, so there we go. That's what we did in class.